Are we recording this?
Yes, we are.
Okay, cool. Then I'll jump in. So, yeah, as Charles said at the beginning of the meeting, myself, Mohammed Alsherman, who's a PhD student under the supervision of our faculty advisors, as well as three core members, Chris, Mahir, and Wanda, have been working on putting together a IEEE letter that we're submitting to the Robotics and Automation journal. And what it's on is the environment modeling techniques that we've been working on, both from a practical setting for winning the competition and also in a research setting of how these techniques can be standardized and, as we say here, enhance behavioral planning. So yeah, let's jump into what we mean by environment modeling and how it enhances behavioral planning. So the big question overall is, why do we need environment modeling? Well, we can start thinking about it from a societal motivation. 40% fatal crashes occur at intersections, and most of the quoted factors are human, distracted driving. So we want to switch over to autonomous agents making these navigations through intersections. But in order to do that, we need safe and efficient behavioral planning algorithms. And a prerequisite for these behavioral planning algorithms that make decisions about how to traverse intersections is we need an understanding of the world that we're making these decisions inside of. So this leads us to really the crux. How do autonomous systems understand the world around them? And before we jump into the details of answering that technical question, I'd like to start out with just a motivating kind of exercise here, which is how we ourselves, how our human brains think about and understand our world. So the exercise is take a minute, look around you, look around your bedroom or office or wherever you are, and really do some introspection on how you understand the state of your environment. And so hopefully you've picked out a few features of your environment and you're kind of thinking about how you understand their state. And now I want to ask you, are you understanding each feature independently? Or rather, are you understanding each feature based on the relationships that it has with other features in your environment? I don't think we need to have an interactive discussion about this, but hopefully with some introspection, you're noticing, for example, I noticed that the keyboard that I was typing on and my mouse that I was moving around, they have a relationship with the desk that I am sitting at. And I understand that this relationship has some properties. The keyboard is on top of the desk, so it has that spatial relationship. I understand the property of the desk, that it is solid. And then by understanding this relationship and these properties, I decide to take an action, which is to keep on typing on my keyboard. And I know based on my understanding that the keyboard will not fall away from my hand. So in the context of autonomous driving, we have a lot of complex states to understand at a busy intersection. And the argument that we're presenting is a good way to encode this understanding is using relationships of the different entities in the scene. Okay, so yeah, with that kind of motivating exercise, let's jump into some more technical motivation. So starting off, There are widely accepted a priori, which means information that is given to the autonomous agent before it actually enters the environment in an online setting. So this is offline information given to the autonomous agent. So widely accepted models for this offline information of the static environment are relationship rich. So for example, lanelet2 and not auto drive, open drive, they encode lane neighboring and successor relationships to relate how the road surface, different features of the road surface are related. Also relationships between traffic lights and the lanes that they control, so relationships between different spatial entities. However, these relationships are handcrafted by humans, and it's a laborious process to create these maps, as I'm sure the HD mapping team knows, and it's something that we go through on the team frequently. However, for dynamic planning and decision-making, relationships between online detections, so information sources that we only observe while the agent is running in an online fashion, so these are from the onboard sensors, relationships between these onboard detections and the a priori model must also be built in real time. However, we found that there's a surprising lack of details on methods for how to do this in the literature currently. So what we want to do is build a standardized method for building relationships between a priori model and the online detections. And this is what our letter really focuses on. So kind of as a visual way to understand what we're doing is using this layer diagram. So on the top, we have the layers that are closest to the real world. And then also the separation from left to right is the left starts out with the a priori information sources. The right is the online data sources. And then as we go down, we see how we combine them. So starting at the top, we have the real world. And in an online setting, the real world is exactly that. It's the physical properties that light reflects off of and that LiDAR bounces off of that our onboard sensors can understand. But from a modeling perspective, a world is a bunch of data points that you can trace out in some map creation software, for example, JOSM. So two representations of the real world. The real world that we encounter as humans, that is perceived by some perception scheme. We're using a variety of neural networks and tracking algorithms to present, for example, a track of a pedestrian as it moves through the world. And then on the other side, on the a priori side, you encode all of these data points into a relational model, like the ones I'm mentioning here. And you can kind of see the schematic for how that works in this layer here. So this is kind of where the state of the art is currently. You have this a priori model with a lot of relationships, and then you just have these feature tracks of different features as they move through the environment. And so the question that we want to answer is, how do you build relationships between these two data sources in real time? And that gets us into these bottom two layers here, where you have the combined physical space of both the a priori model and the online detection scheme. And then you extract meaningful relationships out of that combined physical layer. And these relationships, the goal of them is to enhance your behavioral planning, to enhance your decision-making ability. So yeah, this is what we're really going to be focusing on, is how do you extract these meaningful relationships, and then what impact does that have on behavioral planning? So the main contributions in this regard of our letter are these 3 bullet points here. So a novel and standard method of extending an a priori static relationship graph. So that's something like we have here in our diagram. Extending it with dynamic observations, this layer, in order to create this unified environment model. Sorry, which we show at the bottom here. We also show that the proposed model prevents decision-making complexity from scaling to intractable levels as the complexity of the environment increases. And another contribution is that we argue that the model also allows for online inter-agent verification and offline human verification of the decisions that are made. We're not going to cover this contribution in the presentation, but I will definitely link you guys to the submission that we're making to RAL, and you can read about it in section 4 there. Okay, so before we jump in to the details of the design that give us these properties, let's just go over the overall pipeline that we have in our autonomous stack. So we have our a priori model, which the HD mapping squad creates. This is encoded in the lanelet2 format. We also have the perception scheme, which is here in red, which takes information from all of our sensors and outputs tracks of pedestrians, tracks of different types of signs, the occupancy grid, which is estimation of occupancy around the vehicle, and then also estimation of the ego's state vector, which is necessary for both modeling and control. So this blue box here is really where the magic happens, where our novel contributions are implemented. And this is called our online environment model. Basically, it is a standard way to combine the a priori information with the online detection schemes to form these relational entities, which we'll go into more details about. But there's stuff like, how does the pedestrian regulate different lanelets based on pedestrian tracks? How does intersection signage change the lane connectivity? How does occupancy, again, block lanelets and change the lane connectivity? And all of these relational entities are then queried by the behavioral planner. The argument that we'll be going over in the next few slides is that given these relational entities, behavioral planning becomes a lot simpler than if you didn't have this intermediate model and you directly try to decide on your behavior based on only looking at the online information coming in. So yeah, now let's dive into the details of this blue box here and why it makes behavioral planning a lot simpler. We call these relational entities that we see here the different features of the environment. And now we'll go over exactly how we design them. The pseudocode and C++ code for these designs that I'll be going over briefly is publicly available at this GitLab repository. So definitely check that out if you want more details. Okay, so now let's first go over the traffic sign features. And it's important to note that the features that we will be focusing on are, of course, driven by the deliverables of the auto drive challenge. But the overall methodology can be applied to a wide range of different features. And we'll go over kind of what happens to the model when the complexity of the environment scales up to a wide range of different features. But focusing on this small subset for now, we have the stop sign model, which is illustrated in this schematic here. But in some brief terms, we first generate the candidate set, which in the diagram here is the orange lanelet and the blue lanelet. And this candidate set is based on the radius around the stop sign. So any lanelets whose boundary intersects with this radius around the perceived sign is called a candidate lanelet. Then we also add all of the adjacencies of the candidate lanelets, which includes the red lanelet here, to form the overall candidate set. The second stage, we intersect, so doing a set intersection with the set of lanelets that the ego vehicle is in. So in this example here, this green block is the ego vehicle, and its set would just be this red lanelet. So after we intersect the candidate set with the ego set, we are left with the blue lanelet and the red lanelet, and we call this the controlled set. So doing this intersection, as you can see, it prunes out the lanelets, like this orange one here, that are not regulated by the stop sign based on how the ego is approaching the sign. And to actually form the relationship between the online detected stop sign and the controlled set, we instantiate a lanelet 2 regulatory element, which is the C++ encoding of all of these entities here. They're modeled as lanelet 2 regulatory elements. And then each of those regulatory elements is added to the controlled set lanelets. Then how this impacts behavioral planning, we'll go over that at the next slide. Okay, so I'll go over the next three a little bit more quickly, but we have intersection signage, which is stuff like a no right turn sign. And how we modeled this is we do a forward search starting at the ego's lanelet, which is here in purple, as well as all of the adjacencies of the ego's lanelet. And this forward search is trying to find intersection lanelets. And we know a lanelet is an intersection lanelet based on a priori attribute tag, turn direction. So this search, if the ego vehicle was here, would return the lanelets that are in red. And after we have these intersection lanelets, we match the type of the observed traffic sign to the intersection lanelets that it would influence or regulate. So a no right turn sign would, of course, regulate a right turning lanelet because it's applying a traffic rule to that lanelet, which is saying this lanelet is no longer passable. You cannot drive through it according to this traffic rule. So again, we instantiate a lanelet 2 regulatory element. And in this case, we would add that regulatory element to this lanelet. And in that way, we would model the relationship between the online detected sign and the a priori lanelet map. Okay, so we have this technique expands to other heterogeneous features. So not just stop signs, but for example, construction blockages. It has a relationship with the lanelets that it is blocking. So we first do some logic to check which lanelets the occupied area is blocking. We see if it's blocking all of the adjacent lanelets. So it's not able, we wouldn't be able to simply switch lanes and avoid the blockage. We ensure that all of the lanelets are blocked. Then if that's the case, we instantiate a occupancy regulatory element and add it to all of these lanelets that are blocked. And in that way, during behavioral planning, we would be able to determine that our current lanelet route, which may have turned to the right, is no longer feasible. And we would be able to replan a new route that does not use these blocked lanelets, and that might go forwards. And then lastly, we have pedestrian movement. And to model this, we have the predicted trajectory of the pedestrian given by the tracker. We generate a conflict set, which is either the intersection of the predicted trajectory with the bounds of lanelets, or if the pedestrian is stopped and waiting near a lanelet, that's also considered a conflict. We calculate the stopping points using either the intersection or the closest point if the pedestrian is waiting. And then we instantiate another regulatory element that holds information about the stopping point and add it to each lanelet, which is in the conflict set. So in this way, we've once again created relationships between the online information of the pedestrian track and how it interacts with the a priori model. And we extract the relationship of conflicting from that information. You can see highlighted in red here are those conflicting lanelets. Okay, this would probably be a good time to pause if anyone has any questions that they want to ask now. Okay, then let's move on to the last section, which is talking about how these relationships that we've extracted, how they enable us to reduce the behavioral planning complexity. So to discuss behavioral planning complexity, we do need some notation, but don't worry, it's pretty simple. So we have these three sets that we'll define first. So F is the feature class set. So it holds each of the classes of different features, where C1 might be all of the pedestrian tracks, C2 might be all of the stop signs in our environment, et cetera, et cetera. And we say that there are n distinct feature classes. The B set contains the feature behavior set. So these are the behaviors that each feature could influence the environment with. So for example, if we think about stop signs, the stop sign could influence the environment by enforcing a stopping position. So that might be B1, or it might have no effect on the environment, depending which lanelet we're comparing it to. So B2 could be there's no stop required. And then our last set, E, is our ego behavioral set, which is the actual state of the ego vehicle. For example, E1 might be stopping. So another question is, how do we go from F to E? That's kind of the definition of the behavioral planning procedure. Given the features of the environment, how do we go to a discrete ego behavior? So first we define H, which is a set of handlers where each of these handler functions determines how you go from a certain class of features. So these are all of the instances maybe of stop signs to the feature behavior, which is the impact that that feature set is having on the environment. And then to produce our ego behavior, we need the handler interaction function, in which we take the cross product of all of these handlers in the handler set. And you can kind of think of this as comparing pairwise the outputs of the different handlers and seeing how they interact in order to form a ego behavior. So kind of a graphical representation of this is we have our F set, which is the input into our behavioral planning algorithm. Each distinct feature class in the F set has its own designated handler function. And then the really crux of the behavioral planning algorithm is how we define the handler interaction functions, which take in a combination of each of these handlers and produce a discrete ego behavior, such as deciding to stop or deciding to reroute. So the complexity of the interaction function and how these handlers interact to form a discrete ego behavior really defines the complexity of behavioral planning. And we want to make these this interaction between the handlers and the ego behavior as simple as possible. So in other words, we want to reduce the complexity of this input space of the interaction function. So currently, as you can see, it's scaling up quadratically in terms of the number of feature handlers. And we want to avoid this quadratic scaling by taking advantage of homogeneous behaviors that are common between different sets of features. And on the next slide, we'll show how our environment model allows us to represent these homogeneous feature behaviors and how it reduces the complexity of these interaction checks.
Sorry, can you give an example of an interaction check?
Yeah, absolutely. So let's say we have the two handlers for the pedestrian tracks and the sign tracks, which could be stop signs. So both of these features, we know that as a human, they're going to interact in some way to decide where we have to stop, right? Like stop signs and pedestrians both make us stop as we're driving along, or they have the potential to make us stop. But depending on the spatial interactions of these two features, the stopping decision could look very different. So for example, if the pedestrian is crossing a crosswalk that lies after the stop sign, we might have to obey the limiting line of the stop sign. But if the pedestrian actually deviates a little bit from inside the crosswalk, it's possible that we'll have to stop before the actual limit line of the stop sign. So yeah, this is an example of how the pedestrian handler and the stop sign handler would have to, they have some combinatorial properties where to decide on the actual ego behavior, you have to see how the outputs of the two handlers interact.
Thank you.
Is that okay? Cool. So yeah, here's a more here's another concrete example. I probably should have just used this example because we actually have some code to show about it. But so let's do the case study of our route is blocked, right? Like this is something that can happen as the ego vehicle is driving along. And there's a variety of different heterogeneous features that could lead to a route being blocked. For example, there could be some occupancy grid so that we have a physical blockage, or we have some traffic signs that say you can't proceed along your route. For example, we want to turn right, but then there's a traffic sign that says we cannot do that, right? So our route is blocked. So without using any environment modeling technique, what we would get is two feature handlers for the occupancy grid and the perceived signs. And then we would have this interaction check to decide on the actual ego behavior based on the interaction of these different handlers. So that's what I have written down here. And what we see based on how the interaction check is implemented, we see that the complexity would scale quadratically in the number of feature classes n. And this is because any two features in the environment could have some synergistic interaction that influences the final behavior of the ego vehicle. So it is a kind of a n choose 2 complexity to inspect all of those interactions. And because of this quadratic term, as we scale up the number of feature classes, our ability to implement the ego behavior decision in a tractable way will become impossible. So this is where our proposed environment model comes into play. So in our environment model, as we described in the feature design section, each of these lanelets along our route is modeled as either blocked or not blocked. And what this, and the kind of the complexity of calculating this homogeneous behavior of if a lanelet is blocked or not. Again, it can depend on a variety of heterogeneous feature classes, but the information needed by the behavioral planner is just this concept of if the lanelet is blocked or not. So this blocked or not concept is, if we go back over here, it is the complexity is equal to the size of the feature behavior set. So each of these feature classes could have a different behavior based on how the handler is implemented. And then that comes into play here, where each of the features needs to have a behavioral effect on the lanelet. And in this case, we're only considering features that have a blocking effect on the lanelets. So yeah, using this model, as I described here, the knowledge needed by the behavioral planner, which is if the lanelet is passable or not, stays homogeneous, no matter the different heterogeneous features that you're considering in your environment. And in terms of the complexity, this boils down to now we have this M term showing up, which is all of the different ways that the features could affect the behavior of the environment. So it could be blocking, it could be stopping, all of those different ways it could affect the environment. That's M. And then we need to multiply that by all of the different feature classes that we're considering. But since we're distilling kind of this information down to only the possible effects that the online features could have on our environment, we no longer have to check this pairwise interaction between different features. We only care about the different homogeneous effects that the features could have on our environment. And kind of the key computational advantage here is that M, we claim, is a small constant in all cases. So no matter how complex your environment gets, however many of these heterogeneous feature classes you want to consider, from a behavioral planning perspective, it's still going to be a small amount of impact on the environment. For example, if our route is blocked or if we need to stop along our route. And in this way, the complexity of behavioral planning stays approximately linear. in the number of feature classes instead of seeing this quadratic explosion if you didn't use the environment modeling approach. So any questions about that? I know it was kind of detailed, but hopefully you guys got the overall idea of taking advantage of the homogeneous aspects of the different features in order to reduce the complexity to be approximately linear.
Sorry, could you define like homogeneous and heterogeneous in this context?
Yes. So I'm applying the word heterogeneous to describe the complexity of the environment. So there are many, many features in the environment that would seem to have no relation between them. For example, a pedestrian and a traffic sign, they're not semantically similar, right? So that's what I mean by heterogeneous, is the semantics of the two features, they have no overlapping similarity. A pedestrian is a completely different physical object compared to a traffic sign. But when we look at these different heterogeneous features from the perspective of generating a behavior for the ego vehicle, we notice that they have a lot of overlap in that space, in the B set space. So this is kind of describing the homogeneous effects that each of the heterogeneous features can have on the environment. So it's not truly homogeneous because this set would be 1 if it was a completely homogeneous effect on the environment. But we're claiming that this is approximately homogeneous, meaning there's approximately a constant number of different behaviors that the features could have on the environment. Does that make sense? So this is kind of the heterogeneous set, and then it reduces down to this homogeneous set when we consider the overlapping effects that the features have.
Yeah, I think so. So it's kind of like you're like sort of offloading that stuff that you would do in the behavioral planner before into the environment model, because like everybody needs to use those like individual feature behaviors.
Yeah, exactly. So by identifying these feature behaviors and modeling them in the, if I just go back to the data diagram here. So by having this environment model before the behavioral planner, we're able to assess these homogeneous behaviors so that when the behavioral planner looks at the model, this decision that happens here of synthesizing all of this information together is a lot less complex than if you just look at all of the homogeneous features directly from the perception scheme.
Yeah, I think that clears it up. Thank you.
No problem. Good question. Any other questions about this argument of reducing the complexity of the interaction? All right, so yeah, those are the main ideas, I'm pretty sure, yes, that I wanted to get across today. Hopefully you have a better understanding of our motivations for having this environment modeling layer and how it's making our behavioral decisions a lot more simple to implement. So I'll just finish off here with a demonstration. So this is what the multimedia attachment that we're submitting along with our manuscript, and it's demonstrating the pedestrian feature model. So the pedestrian is in blue here, and as we see it spawn into the scene, it's in immediate conflict with the lanelet that was over here. But then as it starts to move around the environment, it's now in conflict with these lanelets up here, first by moving, but now because it's waiting. And oopsies, did not mean to, just wanted to pause it. And you can see that the effect it's having on the behavioral planning as well, it's cutting off the reference path of the ego vehicle. After a certain period of time, the timer for waiting expires, so we can actually move past a pedestrian that's never crossing. And then as the pedestrian moves away from the intersection, it's no longer heading towards any lanelet, and we don't have any conflicts. So now we're going to do that same demonstration, but this time in a closed loop setting where we're actually using the perception stack. So that's what you're seeing here is the detection of the pedestrian in the camera frame, and then how our tracker predicts the trajectory of the pedestrian over time. And then in this top-down view, we're seeing how that predicted trajectory influences the a priori model, so where it conflicts with, and then how it also influences behavioral planning, cutting the reference line. So at this point, the tracker actually lost its original track, which is this yellow line here. And now we're seeing to the software what looks like a new pedestrian moving through the scene. But after a while, we will realize that we're not getting any information from that old track, and we move it from the model. Then as the pedestrian moves fully past our lane, we're no longer conflicting with it, and the behavioral planner tells the ego vehicle that we're safe to move forward through the intersection. Alrighty, so yeah, thanks for listening and thanks for watching that demonstration. Yeah, let's say we have like 5 minutes for questions before I have to go to the path planning meeting. So yeah, any questions?
How hard is it to extend this model for more interactions and more objects, like cars, for example?
Yes, so we addressed that deeply in the research paper. That's a lot of our evaluation of the model is based on arguments of what happens when we scale up the complexity of the environment. And this is really where our design of our model shines, because if we weren't using the model as we scaled up, so maybe there's more heterogeneous features that influence the routing of the ego vehicle. We would, of course, have our number of handlers scale up. But if we weren't using the model, we would see the interaction check complexity also scale up in a quadratic fashion. So our argument is that under a no model algorithm, implementing behavioral planning decisions would quickly become intractable. But then when we do consider planning under our model, for your case, when we wanted to consider vehicles moving through the environment, that would not lead to quadratic scaling because the vehicles would have the same behavioral impact as, say, pedestrians, right? Like we would have a prediction of where those other vehicles are moving towards, and we could generate a conflict set, just like we do for pedestrians. And therefore, we would still have this homogeneous behavior on each of the lanelets, which is the lanelet in conflict with the other actors in the scene. So in that way, we would still, of course, our n would increase. We would need to implement a new handler for that vehicle class. But since our m, which is the behavioral impact that that new class has on the model, it stays constant. It's either in conflict or not in conflict with some lanelet. Our argument is the behavioral planning decision would stay simple. It would only scale up in a linear fashion because you only have to implement the handle.
Pretty cool.
Any other questions? All right, so yeah, very many thanks for your attention. I know I took up 40 minutes or more of your time, so thank you for that. And yeah, feel free to message me on Discord if you have any follow-up questions. I'd be happy to discuss this more. And if you want to review our letter that we're submitting to Val before we submit it, that would be very appreciated as well. So yeah, just reach out to me on Discord. Have a good afternoon.
Thank you, Ron.
No problem. See ya.